Yeah, thank you very much, Per. Welcome to Project Purple. Our project originates from two papers by Blunck and Kunstmann, which I've always wanted to read when they appeared 20 years ago, but I never came about to do it. So I took the chance of this year's ISEM to offer a project about the topic. And yeah, without further ado, I would like to introduce the team. We start with Eric from Kaiserslautern. Then we have Charlotte from Darmstadt, Siwang from Paris, and Jonas from Mainz. The stage is yours, please.
Yeah, thank you very much, Hendrik, and also a big thanks to the organizers of this year's ISEM, who not only put together a beautiful series of lectures for us to study, but also gave us all the opportunity to present the work of the past month here in this final workshop. So we will present you something on LP extrapolation a la Blunck-Kunstmann, like Hendrik already mentioned. And what this means, I will explain you in a minute. So we start with a well-known object from the ISEM lectures, which is the operator L as defined by the form method as we all know it. And here A is a coefficient matrix which is uniformly elliptic with L infinity coefficients. And let me stress here that we allow for complex coefficients, but I will also comment on that in a minute again. And I have learned that it's always a happy occurrence if we see some semi-groups appear in the talks. So I can excitedly announce that in this talk, a key actor will be the corresponding semi-group, which we of course know always exists. Okay, so let me first introduce the actual main actor of the talk, which will be the vector-valued Riesz transform. So for this, start to observe that, well, the square root of the operator L as defined by the functional calculus, mapping from its domain to its range, is injective. So if we restrict it to the range, then we can invert it. And the inverse then maps back into the domain of the square root of the operator, which by Kato we know is the first order Sobolev space. And hence we can apply the gradient to it and get this map from the range of the square root into L2. And again, using Kato's square root property and the fact that we can decompose L into the kernel of the square root and the closure of the range, but the square root is injective, so L2 is actually the closure of the range of the square root of the operator. We can extend this definition to all of L2, and this will be then our definition for the Riesz transform as an operator on L2. And now a very natural question may be, well, can we do this for p other than 2? And if yes, for which p? Can we quantify this in a way? And let me maybe here also mention that in our talk, a central idea will be that we have the situation p equals 2 is well understood, so we will build on results for the case p equals 2, where we know that they are true and try to extend them to a larger range. And now I will present you the main theorem that we want to prove during the presentation. And this is due to Blunck and Kunstmann from 2003 and 2004. Which reads like this: the Riesz transform is bounded from LP to LP for all p in some interval between some p0 and 2, if and only if this is also true. If and only if the semigroup is bounded from LP to L2 for all or equivalently some p in the same interval. Okay, and you may notice that here we restricted ourselves to the case where we are in the interval between 1 and 2. You can also get results for the other side of the central point p equals 2. But unfortunately, this requires, or maybe not unfortunately, but this requires a different proof. And unfortunately, we will not be able to present you this due to time restrictions. So we focus on one side of.
Consists of bounded operators LP to LP, or really bounded uniformly?
Yes.
Uniformly bounded for T.
I will specify what I mean by this in a minute. It's just to give you an idea what we want to do, but I will make it more precise in a minute. Okay, but first of all, now let me mention this maybe. We have allowed quite general L here, and you can see that, for example, if we take for L the Laplacian, then we have the heat kernel representation, so we get nice bounds on the kernel, and for this we can, for example, show that we actually get this result for all p larger than 1. And likewise, one can show that in case of a real coefficient matrix, this is also true for all p larger than 1. So it's really a crucial point that we allow complex coefficients where things start to get difficult. All right. So now, why do we care about this result? Let me try to motivate this by giving you two examples. I am well aware that filling this motivation section could be a talk of its own, so I will try to be brief. And first of all, say something on the vector-valued Riesz transform. So if the Riesz transform is bounded on LP, this roughly means something like this, right? And then just expanding by square root L and inverse square root of L in between, we can reformulate the inequality and see that somehow we get one side of the Kato square root conjecture from it, one inequality, but this time not on L2, but on LP. And I cannot explain you much about this. Well, if in the case p equals 2, you can use a duality argument to conclude from this to get both directions. And actually, in the case p not equal 2, you can do you can also do something, but I don't have the time to tell you about it. But it's, you see a close linkage to the Kato conjecture. Then why do we actually want to move away from the case p equals 2? Because this is nice, it's a Hilbert space, we're happy if we know a lot of results, so why take the extra effort and move away from it? I brought you a toy example for this. If you consider the heat equation with a cubic forcing term on the right-hand side, and let's assume that we are looking for solutions in the maximal regularity space. You have seen this in various projects before, so I don't think I need to motivate why one might want to do this. And now we see, well, the nonlinearity is in LQ if and only if our solution lies in L3Q. And here I should maybe say both in space and in time. This is a little bit sloppy here maybe. and thus we want the embedding of the maximal regularity space into this space to hold true. And just for sake of motivation, I brought you a theorem that you can use as a black box. It won't be of relevance further in the presentation. It says that, well, we have this continuous embedding of the maximal regularity space into L3P, and then you have this Bezoff space here in the space variables. And if you know something about Bezoff spaces, this gives the condition that we want this algebraic relation to be fulfilled. Okay, so if you weren't able to follow this, don't worry, it's just for sake of illustration that if you do the computations, this is what comes out. And here you see that, for example, in 3 dimensions, putting q equals p equals 2 will not satisfy this relation. So this maybe motivates why we want a little bit more flexibility in our parameters in order to treat nonlinear evolution equations. Okay, and now let's move on, and I will give you 2 definitions. You have already seen that in our main theorem, we want to link the semigroup to the LP L2 boundedness of the semigroup to the LP boundedness of the Riesz transform. So we will talk about the semigroup for a minute and study what we can say about it before going on with continuing to the proof of the boundedness of the Riesz transform. So we say that the semigroup is LP LQ bounded for some parameters p and q if for all positive t and h from both L2 and LP we have this usual bound, but with some extra decay in the parameter t, where this notation gamma pq is adopted for the Sobolev gap. And maybe let me comment on this here. You will also see it on the next slide. We have this factor 1/2 here, and this is due to the fact that we want to adopt the correct scaling, which is somehow in the order t to the power 1/2, which will not be discussed in detail in the presentation, but it will appear in Jonas's part later on very shortly. So maybe you can look out for this. And then a key idea also from the ISEM lectures was the application of off-diagonal estimates. So let's say what we want to call off-diagonal estimates. Namely, the semigroup satisfies LP LQ off-diagonal estimates for some parameters if there exists some constant independent of all the parameters that follow, such that for all positive t, all closed sets E and F and H from L2 and LP with support in E, we have this estimate linking the LQ norm of the semigroup on the set F to the LP norm of the function on the set E. And again, we have this polynomial decay in T right here, but additionally, we have some exponential decay in the distance of the sets E and F. And here, the difference to our definition from the ISEM is that we have a square here. And again, this comes from the fact that, well, hidden here is the sort of the scaling of t as growing with the square root, right? So this is why we add this additional square here and sort of get some Gaussian decay in this way. Okay, And now we can say the following on the semigroup, namely that for the interval we will consider, so for p between 1 and 2, LP boundedness of the semigroup implies LP, so LP boundedness here means LP boundedness, right? Implies LP L2 boundedness of the semigroup. This in turn implies a Q L2 of diagonal estimates for some Q larger than P, and then from there we can go back to LP, or in this case, well, LQ boundedness, I should say, for the semigroup. So we have a nice circle of implications, but we have to pay a small price in the integrability in the second step. And I want to present to you now the proof of the first two parts, which will be will be used later on in our talk. I will skip the proof of the third part because it's not necessary for us later on. Okay, so to start, we assume LP boundedness of the semigroup, and for t greater 0 and f from both LP and L2, we begin with a version of the Galiardo-Nierenberg inequality, which allows us to link the L2 norm of a function with the gradient of the L2 norm, the L2 norm of the gradient of the function, and in product with the LP norm of the function. And since we want to talk about the semigroup, let's plug this in. Yeah, let's actually talk about the semigroup applied to this function f. And we also have to, because this is some sort of interpolation inequality, we also have to add the correct exponents, and I will just put them in a way which will be convenient for the further calculation, but it's easy to verify that this is just the usual formulation as you may know it. I put it like this. We add a power 2 of alpha here, then, here, no, it's... No, it's supposed to be like this. Yes, yes. And I should tell you something about the relation between alpha, beta, and p, namely in the sense of the interpolation spirit of the inequality, we want alpha plus beta to be equal to 1. And then the Sobolev gap from p to 2 should be given by alpha over 1 minus alpha. And using the first relation, we can also rephrase this as alpha over beta.
Yeah, I think the second exponent needs to be 2 beta divided by alpha.
Yes. Yeah, sorry. Like so. Okay. All right. And now, first of all, let's treat this term. Using ellipticity, we can reformulate this as 1 over lambda real part of this. And now, simply by definition of our operator L, this is the same as 1 over lambda real part of L applied to e to the minus TLF, e to the minus TLF. And here we can make use of the fact that this expression now is actually the time derivative of our semigroup. So here it is crucial that we actually treat the semigroup and not some other linear operator. And then using the chain rule, we can rephrase this as the time derivative of the L2 norm squared of e to the minus TLF. All right, and now for the second part, or for the other factor, we can use our assumption of LP boundedness, and estimate this by the LP norm of F. And here we can use this relation to rephrase the exponent as 2 over the Sobolev gap from P to 2. And note here, we do not have an additional factor in front because the Sobolev gap from P to P is just 0. All right, and if you now look what we formulated is that here we have the time derivative of some object. Here we have the same object, and this is independent of the time. So we can treat this in some sense as differential inequality in the parameter t. And solving this, we then get a relation for this expression given by some constant times t to the minus Sobolev gap from P to 2 times the norm of P, the P norm, LP norm of F squared. And here, if you do the calculation, you see that very nicely this exponent just translates into the square, and then this gives us exactly the estimate that we want, the PL2 boundedness as defined previously. Okay. For the second step, let's again fix t greater 0 and f from LP intersected L2. And maybe I should say we want EF to be some closed set, and we want the function f to have support contained in E. Yeah, as we do for off-diagonal estimates. And now the expression that we want to estimate for our off-diagonal estimates is the L2 norm on the set F of the semigroup. Yes, and we can do this in two different ways. Namely, first of all, just dropping the set F certainly only increases the norm. And now using the assumption that the semigroup is LP L2 bounded, we can estimate this as t to the Sobolev gap from P to 2 half LP norm of F. And since we assumed the support of F to be contained in E, we might as well add the set E here. Also, we can estimate the same expression, this time using L2 off-diagonal estimates, which, as I mentioned before, we say that we have understood the L2 theory, right? So we have L2 off-diagonal estimates for the semigroup at hand. And thus, get the following usual L2 off-diagonal estimate. Like so, for some constant c. And now the idea is to interpolate these two estimates with Ristorin just in a way where when we fix some parameter q between p and 2, we end up with the LQ norm. So we just choose our interpolation parameter in a suitable way so that we end up in the LQ norm. And then, of course, the factors in front will also interpolate. And if you do the calculations, so if you do interpolation here, you see that this will actually simply change the exponent here to gamma q2. And this will only receive an additional factor here, so we can just alter our constant c to some different constant. And then we have f of LQ A. And again, this concludes the proof of the second part. And let me mention one last thing. You see that here we did not use the fact that we have actually estimated some semigroup expression. So this could have been done for any other LP-L2 bounded operator as well. And likewise, in the third step, this is also true in a way more general sense. So only in the first step, we really needed that we are treating the semigroup and not some other operator. Okay, and with this, I have now set up a relation for the semigroup, and I hand over to Charlotte, who will now present us the first part of the proof of the main theorem.
Okay, so as Eric mentioned, the heart of our presentation is to prove this theorem. And here we have two directions to prove this. And I will start with the first direction, which is maybe more immediately to go from the boundedness of the Ries transform to the semigroup. And then Sirang and Jonas have to work a little bit more to prove that if we have LP-L2 off-diagonal estimates for the semigroup, then we have the boundedness of the Ries transform. And as we saw in the result before, this is enough to finally prove this theorem. So first I will start with an observation that the semigroup is LP-L2 bounded anyway for some p in this interval, where 2 lower star is the reverse Sobolev conjugate, and so this means L2 lower star is 2. And so why could this be true? What we know is that the semigroup is L2 bounded and its gradient is L2 bounded. Either you know this from semigroup theory, or I will present you some argument. Similar, we saw this in the lecture for the resolvent, that the gradient of the resolvent is L2 bounded. And so if we have L2 bounds for the gradient, this gives us L2 star bounds by Sobolev embedding. Or again, we can here use Gallardo-Nirenberg inequality, which we know all from the exercises in this formulation. And here Q is in the interval 2 to star, where we define 2 star by infinity in dimensions 1 and 2. And we could also include infinity in the case dimension 1, but we won't need it. And here theta is some constant which depends on Q, and it's actually this Sobolev gap you saw defined before, gamma to Q. Okay. And when we have this, then we get LQ bounds as LQ norm bound estimated by L2 norm. But this is exactly the wrong direction we need. So what helps us here is to use duality and which changes the order and give us some additional Hölder conjugated index. And so if this is an argument we saw also on Monday, and here the adjoint of the semigroup is the semigroup generated by the adjoint operator, and this is again an elliptic operator, and we have all results we need. So let's start with the proof to check that we have the right t exponent. So we take some f in L2 and calculate the Q norm of the semigroup. And since we will prove it at first for the adjoint operator, we take Q in this interval 2 to 2 star. Then Gallardo-Nirenberg gives us these two norms, where we observe that this is really an H1, since the semigroups maps into the domain of our operator, and this is included in H1. And here again, same idea as before. The semigroup is L2 bounded, and here we can use ellipticity. To get this. Next, we can estimate this scalar product by Cauchy-Schwarz. And again, using L2 boundedness of the semigroup, and for this term, using bounded H infinity calculus for the function g equals z multiplied by e to minus z, and this is in H infinity, so we get an additional t to minus theta half times L2 norm of f, and as we saw, this theta equals our Sobolev gap, and this completes the proof. So in order to prove the necessary condition, we saw that for dimension 1 and 2, there's nothing to do. And for the other case, I will give some remarks. First, if the Ries transform is bounded on LP, then the operator L minus 1/2, which maps from its domain intersected with LP to W12, satisfies the following estimate. So we can extend this operator from LP to LP star. Yeah, there's more to do, but it's enough to agree that we can extend this by density argument. And also, we know by Ries interpolation, which you have seen yesterday, that if we have the Ries transform as LP0 bounded, then by interpolation it is LP bounded for all P in between. So with this, I will start the proof by drawing a picture. So dimension is larger than 3. And what we know is that the semigroup is L2 bounded in this interval, and we pick some P0 here. And for this, we know that the Ries transform is LP0 bounded. So by the remark above, we know that L minus 1/2 maps boundedly from LP0 to LP0 star. And we would like to get the connection from LP0 in this interval. So what we can do is iterate this argument and get in total that for some k, the operator L minus k/2 is bounded from LP0 to LPk, where Pn is defined as the Sobolev conjugate of Pn minus 1. So what we get is that the semigroup applied to L minus k/2 is bounded operator from LP0 to L2. But here it remains to argue why this additional operator is no problem. And here we use functional calculus and write the semigroup at time 2t as follows. This operator is h infinity 0, so this is bounded from L2 to L2. And here we need, again, an additional power of t. So this is by functional calculus, and this is true at least for all f in the domain of the last operator intersected with LP0. Okay, this is good, and so we can estimate the L2 norm. This is bounded, so makes no problem in L2 norm. What we get is L2 norm this function, and here the semigroup is LPK L2 bounded, so this gives us L minus K half F in LPK norm with an Sobolev gap PK2 half. This operator is bounded from LP0 to LPK, so we can write here P0 norm. And now from the picture and the definition of this PK, we see that K plus gamma PK2 is exactly P0 to what we need. So this would finish the proof, but we take F in this intersection, and again we can argue by density argument, which is not immediately but technical, so yeah, we skip this part and finish the proof. Okay, so yeah, I hand over to Simon.
Hello everyone. So as the title suggests here, I'm going to tell you something about criteria for LP boundedness of an operator. And my part will be a little bit rather independent from the rest of our group because there are no semigroup involved here, unfortunately. I'm sorry. And the goal of this part is to introduce the theorem for Blunck and Kunstmann that my groupmate Jonas is going to use afterwards to study the LP boundedness of the Ries transform. And I'm trying to share with you some of my not so humble interpretations of this theorem since Professor Kunstmann is here with us today. So in order to motivate everything, let's start with a very simple example. So the criterion for the convolution type operator, when this operator T admits a convolution kernel K, we have the Young's inequality that tells us this operator is LP, bounded from LP to LP as long as this kernel K is integrable, so it's in L1. This property is very nice, but unfortunately, not all the kernel falls in this class. For instance, the Ries transform associated to the Laplacian does not satisfy this condition since it has explicit kernel, which you can see here, it's almost L1. Unfortunately, because it's only in weak L1 since it has two singularities at 0 and at infinity. But fortunately, we can hope that it's still bounded from LP to LP since it's belongs to a larger, it belongs to a certain class of operator called Calderon-Zygmund operator, which you have seen on Monday. So in this case, it turns out if this operator T is a priori bounded in L2, the singularity of the kernel at 0, that is less problematic. So in a sloppy way, we can just define our operator via this actually oscillatory integral here. And in this case, we have a so-called compensated L1 condition for the LP boundedness of the operator, and which the Calderon-Zygmund operator satisfies. It's called the Hennenfent condition. So we have this proposition that tells us that if the kernel K is associated to an L2 bounded operator T and it satisfies this additional assumption, then this operator is weak type 1,1 and that's strong type PP for any P in 1 or 2 by the Marcinkiewicz interpolation theorem, which you must have seen in the ISM exercise part. So before we move on, I would like to tell you more about what this Hennenfent condition means. So you may wonder this integration area x, the distance between x, y, and y larger than 2 times the distance between y and y prime. This might be a little bit confusing, so let me draw you a picture. So if we take y here and y prime here, we should draw a ball which the 2 times of the radius, 2 times the distance of y, and y prime is not very round, but okay. So S should lay out of this ball. And this condition tells us that the kernel evaluated at 2 points here, y and y prime, this difference is integrable with respect to the other component, which is x, at infinity. So this might still be a little bit confusing to some of you. So let me show you another integrated version of this Hennenfent condition. If we pick up a ball, B equals to BR here, we integrate, we put in some F1 function, F in L1 function supported in this B, and we integrate this over y prime on this ball and over x here. We will have this integrated version of Hennenfent conditions, writes like the t act on some compactly supported and mean zero function. It decays at infinity in an integrable way. So again, by this here, by infinity, I mean which is far away from the support of f. So this is actually an integrated version of that. It's almost, they are almost equivalent, and here you can see that this is also a projection to the mean zero space. And another way to put this, to read this condition is that the t, if we approximate this f on its boundary by its average, the t acting on the approximating error is decaying at infinity in an integrable way. So it should be harmless, and this guarantees us the weak type 1-1 boundedness of the operator. But still, unfortunately, there are a lot of operators that does not Cardinal-Zygmund operator, namely, it does not admit a kernel, for example, the Ries transform associated to the elliptic operator in divergence form. And so we actually need finer tool to analyze the LP boundedness of the Ries transform, which is what we are studying now. So in the next part, I will show you how we push this Hennenfent condition into a kernelless case, and then I will prove you this proposition to motivate our proof, and also as a complement of the T1TB theorem presentation on Monday. And in the end, I will tell you how to adapt this proof to proof of the theorem of Blunck-Kunstmann. So let me show you, let's just have a peek of the theorem that I've been talking about. So assume that T is a bounded operator in L2, which we will choose to be the Ries transform afterwards. AR be a family of linear operator. It's actually a family of averaging operator at the scale R, and which we are used here to replace this local averaging of F. And P is, and so we will use this ARF to approximate F on its boundary, so on this B. And assume that we have these two estimates that take a lot of spaces here, and we will have the operator as weak type P0, and thus strong type PV still by the interpolation theorem. So before I give you more intuition about what this two estimate is, you must have seen something similar here. It's the CJB. Again, it's nothing but the annulus and the balls that we use in the ISM lecture. So we define here C1B is equal to 2B. I mean, given that we have a ball B equals to BR still here. And the C2B is 4B removed 2B, and in general, CJB is 2JB removed 2J minus 1B. So it's essentially a family of annulus that covers all RD. So the first condition here tells us that when we are away from the support of F, the average of the operator acting on the approximating error is its average is controlled by this Gj, and thus you might notice this summable condition on Gj is nothing but an integrable condition of the decay of this T acting on the approximation error, because this 2 power JD is nothing but the measure, something comparable to the measure of the annulus. And the second inequality, it tells us that since we are using AR to approximate F on its support, it's now here it's no longer compactly supported, so we need to analyze its decaying speed, and still it tells us, this integrable condition tells us that this function is still decaying in an integrable way, so it is harmless. And before we move to the proof, I will just mention that this first estimate is also called a weakened Hofmann condition. This is because first because first by applying Herder's inequality to the left-hand side of this inequality, which I would call the integrated Hofmann condition, we will easily assume that we have this thing. We will easily recover this inequality with with here L1 norm replaced by the P0 norm, and here the locally averaging operator replaced by ARF. And it's weakened because you see there's nothing on the kernel. It does not require the kernel to exist. So it's called the weakened Hofmann condition. And now in this part, in the next part, I will give you some proof of the weak one boundedness of the operator T under this assumption. So actually the key ingredient of the proof is the Calderon-Zygmunt decomposition. So it says that for any f in the LP and some level yet to be chosen T larger than 0, there is a countable family of disjoint cubes that locates the singularity, I would say, of f, and the family of function bi with bi supported in Qi, and it's actually in LPQ, and the function g in L infinity RD such that it's a decomposition of f into good part and bad parts. So this is g and b, what g and b stands. In addition, we have some extra good properties of these functions. So the first, we see that the bi is of average 0 on its support, and its LP average on its support, it's controlled by T. And the G is good because it's in L infinity, and the infinity norm is controlled by T. And the LP norm of T, of course, it's not so large than the LP norm of F. And finally, the set that F is singular, it's also not so large. It is controlled by T power minus P times the LP norm of F power P. So the proof of this is needs some stopping time argument, and as some groups that mentioned some variant of this decomposition previously, I'm going to skip the proof. But I will still give you some interpretation or some intuition about what this decomposition is. So this actually is a very constructive and nice way of writing the decomposition. Namely, LP is included in L1 plus L infinity. So normally, if we do this kind of decomposition, we write a function f in LP into f times indicator function of the set where f is larger than t, and plus f times indicator function where f is smaller than t. And so this function is in L1, and this function is actually in L infinity, as you can easily check. And here you should imagine that G is somehow looking like this part, and the sum of somehow Vi is looking at this part. And moreover, this Qi, the union of all Qi, you should consider this to look somehow not bigger than the set that f is larger than t. In this way, almost every property here you see in these 3 lines, except for the mean zero property of bi, just recovered essentially just after some Markov inequality. So this is almost, this is how you should think of this decomposition. So with this decomposition in hand, I am going to tell you about how we prove this weak type boundedness of T. So this from this and this. So our goal is to prove that the set that f is larger than t is the measure of this set is smaller than t minus 1 f for any f in the L1 Rg. Yeah, so this is the definition of the operator being weak type 1,1. And of course, we would like to apply this Cardinal-Zygmund decomposition by noting that f is equal to g plus some I over bi, and with p equals to 1 and t is equal to this thing. And so by triangle inequality, we can estimate the left-hand side of this targeted inequality by Tg by the set where Tg is larger than T over 2 times the set where T, this sum I bi is larger than T over 2. And we will write it as 1 plus 2.
Excuse me. It seems like you're shooting for L1 estimate at this point, right?
No, weak type L1, weak type 1,1, yes. Yes.
Okay, so how is this related to, you seem to be working in LP or?
Yes, I take p equals to 1. I'm sorry, I should have written it. Yeah, and so we write it into 1 plus 2. The first term is very good, as it suggests, because the function here is good. So we will just estimate by the L2 boundedness of the operator T. So again, by Markov inequality, this is controlled by the T power minus 2 times the L2 norm of Tj, and it's controlled by this according to the L2 boundedness of T. And by applying this, the property on G on the second line, by picking p equals to 1, we will have the desired estimate. The second part is a little bit more complicated, but it's still under control by that integrated version of a Hennenfent condition. So in order to estimate this, we separate this set into two parts. Since we only have this estimate away from the support of the function f, so here we choose them to be bi. So we will separate into this set into two parts. One part is the part which is close to the support of each bi, and one part is away from this bi, so it's this set larger than T over 2 intersect with the complement of the support of this group family of bi. Yes. And this term is very good since we have the last property on the control of the size of the singular part of f. It's smaller than T minus 1 f. And the second part, we can bound it first by Markov inequality and then by this integrated version of Hennenfent condition, namely we will have something like QIC TBI. So this thing by that, so let me just tell you that this here, since we have this Mesier condition on BI, we wanted to approximate BI on its support by its local average on its support. I'm sorry. So actually, this is this function is the T acting on the approximating error. So we can use that inequality to control it by, forgot this sum over I. And we control this by the L1 norm of BI, and by using the second property on the BI, we will know that this is actually, we have the desired bound. And in this case, this way we prove that the Cayley-Zygmunt operator, or more in general case where the operator admits a kernel that satisfies the Hennenfent condition, it should be weak type 1, 1. And the next part, I will tell you about how we adapted proof to show the theorem of Blunck-Kunstmann. And I will provide you a idea of how we do it. So here, like I said, from the first inequality, we can recover this by this local averaging average of f replaced by AR f, and P by P0, R1 norm by P0 norm. And so actually everything goes well here if we replace BI, the approximating error, like I mentioned, by I minus AR BI. Here R is chosen to be the diameter of the cube, QI. RI, sorry. So everything works almost the same. I forgot to mention, we changed 1 to P0. Yes, and everything almost worked the same without, we just changed some of the exponent 1 to P0, and eventually we will almost get the same. However, here, since that we no longer have this mean zero condition on this AR, on BI, we cannot use this more like. So this will give us the extra term here looking like T sum ARI BI is larger than, T over 3, let's say. And in order to estimate this term, we would like to remove the T by its L2 boundedness. So again, by Markov inequality, we will obtain something like this. And again, we can remove this T. So eventually, we will estimate this approximation of this thing in the whole space. But it's very tricky because in the first glance, one may want to apply the triangle inequality to estimate this on each annulus, like the second inequality. But actually, you cannot do that because it's too rough by directly applying the triangle inequality. So the idea here is to linearize this integral by using duality. So we pick some U in the dual space of L2, which is also L2. We will integrate this function, test it against U. Oh, this is actually equals to. And afterwards, we'll, 2. And after that, we can apply this estimate on each annulus, and eventually we will obtain that we can control this by the norm of UI. In this term, there's involved some maximal function of U, which is very technical, and I don't have time to prove this here. But eventually, we will get some bound like this, and it's controlled by the P0. FP0. So it's basically the idea how to prove this theorem, but I skipped many technical parts. And in the next, my groupmate Yunus is going to tell you how we use this theorem to study the LP boundedness of this transform.
So I got the first thing done to work with the microphone, so that's good. So I hope nothing can go wrong now anymore. So what I want to show is that when we have LP L2 off-diagonal estimates, that then we have LP tilde boundedness of the Riesz transform when P tilde is slightly larger than P. And note that by the theorem that was presented by Eric, this LP L2 off-diagonal estimates, they are, let's say, roughly equivalent to LP L2 boundedness of the semigroup and LP boundedness up to some small change in the exponent. Okay, and what we want to do is somehow implied by the talk by Siwang. Namely, we want to apply the LP extrapolation by Blunck-Kunstmann and to the Ries transform, so this will be our operator T. And so we need some operators AR, and we choose them in this, let's say, maybe strange-looking way. And there are two questions, or maybe three questions, that you may ask. First, why does it look like this? Why do we have R squared here? And why do we need that M is large enough? So for the last two questions, I can give you two answers, because, well, we have two estimates that we need to show. Firstly, we need to estimate the L2 norm of ARF on the ball, on the ball and on all annuli. This will will show you why we need R squared. And the second estimate, we need to estimate T to the T minus AD, T applied to identity minus AR on F, but then only on the annuli, and I will show you later why this really only works on the annuli. There we will see why we need M large enough. Okay, so let's start with the estimate with maybe I don't know if you can say easier, but maybe it's easier, of ARF on all balls. There we note that that in the definition of the AR, we can just multiply out the binomial theorem, and then the identity in front cancels out. So AR is just, in fact, or can be written as a linear combination of semigroups at time kr squared. And so, okay, then we can just apply the triangular inequality and then use the off-diagonal estimates that we have on the semigroup. So this gives us this term. So why do I have this marked in red? So first of all, because here I cheated a bit, because this exponential, of course, doesn't appear when j is equal to 1, because then we estimate ball versus ball. But this is only one term in j, so this we can just forget about. And maybe the more important thing is that this shows why we need R squared. Because in the off-diagonal estimates, the distance appears in order 2 and time with order 1. And so because the two sets have distance roughly of 2 to the j r squared, 2 to the j r, we also need time R squared here. So, and then we take what we all can, now we want to simplify this, and we can forget about this k, because k is running from 1 to m, and then we can just delete it. And moreover, we take everything out of the sum that doesn't depend on k, so this will be just some constant depending on m. We have the LP norm of f, which is also good because we want this. And then we have this exponential decay, which will become important in a second. And lastly, we have this additional factor in R squared here. And this is also where the scaling that Eric mentioned before will become important, because in the assumption of Blunck-Kunstmann, we need not only the L2 norm, but we need to take an average again. So what remains here with so this 2 here cancels out, and this 1/2 part goes on the other side. So here it's with plus, but taking our side gives a minus again. And d over p, this is just what we need here. So our coefficients gj are in fact just given by that. Okay, I omit this constant here because it's not important. And then for the summability condition that we need to multiply with 2 to the jd again. But okay, then we see this is still converging very well because we have this exponential here, and j equal 1 again doesn't matter. Okay, so now let's turn to the second estimate where we need to control t applied to identity minus ARF on this annuli. So recall that we have this we have chosen AR in this way. So taking identity minus AR again skips this identity here. So we have this, and now this inverse square root is a bit, let's say, annoying in order to estimate things. And there, maybe you recall the representation formula by Blunck-Kunstmann that we saw in the ISM lectures, and then we can use this after some work to show that in fact we have this representation formula. So what changed here? We got an integral in time from 0 to infinity. Moreover, we have a semigroup, and we have 1 over square root here. So again, we use the binomial theorem to simplify this term, and then also take take the gradient of the semigroup inside. Okay, and here we can also apply the semigroup law. So this term is just the semigroup at time t plus k r squared. And now this is what we want to do. When we now want to do off-diagonal estimates, this is a bit annoying and we want to have it at time t. So what we do is we do a shift in t. So we replace t plus kr squared by t. This means that here we will get a minus kr squared. And also this integral, which before it runs from 0 to infinity, will only run from kr squared to infinity. And then we have the following representation that we can introduce this function ar squared, where everything that I just told you is in. So we have 1 over square root here, and we have the indicator function from kr squared to infinity. Okay, so why is this good now? We need to do one further step here, namely that we use the semigroup law on e to the tl to split it in t, because we want to use LP-L2 off-diagonal estimates for the semigroup, and before the gradient was bad. And then we also, for scaling reasons, we need to have an extra square root of t there. And for this, we have LP-L2 off-diagonal estimates. Here we have L2L off-diagonal estimates. And then one can convince themselves that when you take the composition of two operators that satisfy here LP-L2 off-diagonal estimates and L2 off-diagonal estimates, that then the result again satisfies LP-L2 off-diagonal estimates. So this term is also fine. Okay, the square root of t, this we cannot simplify at this point anymore. So the only thing that we still need to control is this guy here. And this will be my next estimate. Okay, let's do that. This is what HR squared was given by. And we do this in the case distinction t. First, we consider only small t. Small in the sense that t is smaller than m plus 1 r squared. So m is this integer, this natural number that we still need to fix large enough. And when t is larger than m plus 1 r squared, then in particular we can find some natural number n such that t is between n r squared and n plus 1 r squared. And then for such t, the sum doesn't really run up to m, but only up to n, because otherwise this indicator function is just 0. And then what we can do is we can estimate here this k in 1 over square root by n, take this out of the sum, and then what remains it's just again some constant, and we don't really care about. Okay, so it remains to deal with the case when t is large, so larger than m plus 1 r squared. And here I claim that we have this estimate, namely that we can estimate h r squared of t by the radius to the power 2m and t to the minus m minus 1 over 2. So, and this will be the consequence of a much more general lemma, which I present here in the lower part. So what we do here is, again, we'd have some natural number m. Okay, this will be just the same. We have some shifting parameter that for simplicity is just s and not r squared, and this should be positive. And last, we have some m times continuously differentiable function v. And then what this lemma says is then that when we take a weighted alternating sum of shifts of this function v, that then we can bound this by the shifting parameter to the power of m times the L infinity norm of the nth derivative of our function, and on a set where the lower and upper bound just depend linearly on t. First, let me convince you why this is a good lemma, and then come to the proof later. So as I said before, m is just our same m, s will be r squared, and what is about this v? So note when t is large enough, so larger than m plus 1 r squared, all these indicator functions will be 1. So v will just be 1 over square root, and then you just need to be able to take the m derivatives of 1 over square root and get this factor, and r to the 2m is just the shifting parameter to the power m. Okay, so now let's prove this lemma. There are several ways how you can prove it, and we want to use a proof that was where the idea was given to us by Hendrik. And here we do the following, which at first glance might seem a bit random. So what do we do? So for a function f, that is, let's say, first only continuous, defined on 0 infinity, and some t large enough. We define an operator in the following way. We define df of t as f minus the shifted version of f, and s is still this parameter from the lemma. Okay, what can we say about this object? Okay, then when we take norm, I should have C1 here, because now when we want to estimate this, I want to apply the mean value theorem here, and there C1 would be useful. Then what do we get? We get a factor of s, and we get the L infinity norm of f prime on t minus s up to t. And moreover, this definition of d is quite nice, because what happens when we take the derivative of df, then this is just d applied to the derivative of f because of linearity of the derivative. So okay, but now why am I doing this whole stuff? The nice thing is that, in fact, hs of f, hs at time t, where h is now just defined as in the upper part of the blackboard, this is just given by claim that this is like applying d m times to function v. So now v should be in Cm, and this is just v as in the formulation of the lemma of t. Okay, and there are different ways how you can see this. You can just do an induction here over m, but what you can also do is note that this is just identity minus the shift, and then take this to the power of m and apply the binomial theorem, and then this is just what it is. Okay, so we can take absolute values here, and then iterating this estimate, we get the shifting parameter m to the power of m, and the mth derivative of v in L infinity over which set, so over the set t minus ms up to t. But this is not the lower bound not yet the lower bound that we want. But again, we know that t is larger than m plus 1 times s. So we can divide by m plus 1, plug this in here, and then we see that t minus ms is in fact larger than t divided by m plus 1. And this is just the lower bound that we need. Okay, so we have dealt also with this strange guy HR squared. And now we can plug everything in. Can you take it? So here, what terms do we have here? So again, I take case distinction whether t is small or large. And these first terms here, these are the ones that we got just from estimating HR squared. This t to the minus 1 over 2 is the 1 over square root that we added for off-diagonal estimates for the gradient. And then what happens again here, this is the off-diagonal estimates that we got by composing. So why is it important that we have j larger, at least 2, and not, why does j equal to 1 not work? Okay, so what happens if j is equal to 1? Then this exponential function here doesn't occur, because there's no distance between 2 times the ball. So the distance between 2 times the ball and the ball is just 0. And the nasty part then happens when k is equal to 0, because then we integrate from 0 to r squared. And what happens in our integral, so this exponential decay isn't there. This is just 1 over square root. There's 1 over square root, and there's more decay in t. So this won't be integrable in 0. So this is why really C1 is not possible here, and we can only do it for j at least 2. So again, you might think, okay, k equal to 0 might be nasty anyway, But this luckily isn't the case because we can substitute S as 4 to the j r squared divided by t, and then everything works fine. You might just need to calculate a bit better than me than to do it in the rest of the lecture. This is good for k equal to 0. When k is at least 1, we can just forget. Then in this term, we can just plug in the lower bound of the integral and integrate this integral explicitly, and everything is fine. And in this case, we do the same substitution, so S is equal to 4 to the j r squared divided by t. And when we do all this, we get the following estimates. And you might wonder where this 2 to the minus j to m comes here from. But this is not really a problem because we have exponential decay in j here, and then we can generate as much polynomial decay in j as we want. And this is, so why is this good? So when we plug this all in, here in order to estimate everything here, we also need some Minkowski inequality for integrals, but then we can plug in this inequality and obtain this. Here the scaling factor in R is exactly the same as when estimating AR squared, ARF. So this again takes care of the averages here and here, up to this factor that is occurring here. And now for the summability condition on the GJ, we again need to multiply with 2 to the JD. This means that this minus here will be a plus instead. And then in order for the series to converge, we need that 2m plus gamma p2 is larger than d over 2. And so we need to choose m large enough such that this inequality is satisfied. And when we have this, then we can run the LP extrapolation theorem and get, in fact, LP tilde boundedness for the Ries transform. So in total, let me recall what we proved. We proved that the Ries transform is bounded on LP for p between p0 and 2, if and only if the semigroup is bounded from LP to L2. And with that, I want to conclude our talk. Thank you very much.
So thank you very much for this very nice presentation. Do we have questions? Yeah?
Sorry, which page?
7. The right-hand side of the first equation minus or no? I think this is fine.
Why?
If there one minus, I could relate it to bipolar model as it is normal criticism. But with no minus, and I wonder, or can solve it as it is.
What? Can you explain?
Question, I mean, the first equation, yeah?
Yes.
You have partial time, u minus Laplacian, and then u equal u3, yes?
Yes.
I wonder if there should be minus u3.
Yeah, maybe, but I.
It is necessary. I mean, this minus has some coercivity problem, yeah, property, and then it is very essential when it comes to solving such a PDE or SPD, whatever. And this minus is very essential. That's why I'm asking: should contain minus or no?
Let's discuss this afterwards, maybe.
Okay, next question, Sebastian.
Yeah. So Eric, in the beginning you announced that we finally will see some more semigroups.
Yes. I mean, in my part, you did, right?
We saw many semigroups, but the lecturers also showed us that often you can do stuff with resolvers instead of semigroups. So
yes.
you think a bit about what happens if you develop a theory with resolvers instead of semigroups, like stuff that becomes more complicated, stuff that becomes maybe easier.
I mean, it's a very good question, but
So please correct me if I'm wrong. So I think it's totally possible to develop this theory by using the resolvent, because as far as I am aware of, I think Moritz and Pascal has a paper on the solvability of block-formed Dirichlet problem, and where they use the resolvent to do everything. And I think it makes it more difficult because the resolvent is only regularizing little by little, but in semigroup could go very well. I mean,
the resolvent has no semigroup. Yes. When you use the semigroup law, it makes your calculations easier. You can do it with resolvents, but then you have to keep track of an additional parameter. You have to take tremendous powers of resolvents. It's a mess all over the place. So keep your hands away from this until you switch to a setting where there's no semigroup anymore.
Further questions? Moritz?
I mean, I could ask. You said at the beginning you want to give us some motivation why we should study retransform in LP spaces, and then comes this slide. Is there any relation between the two things?
Let's say maybe this slide was only meant to motivate why we don't only want to consider the case when p is equal to 2.
Yeah, I think I misunderstood your question. So here there is no retransform involved, of course. It's just to motivate in a toy example why LP theory for PDE might be useful in general. And I tried to give the other example with the connection to the Kato square root conjecture to show why retransform is interesting, but then to get these two things together, I think is not so easy to explain in a few minutes maybe. So.
Okay, further questions? Yeah, Patrick?
I just have a short comment on slide 10. You left out the maybe it's slide 11. No, with this,
sorry.
With this circle.
Yes.
Okay. There you left out point 3, right? I just wanted to comment that actually this was what we presented in the lecture notes. We did it for the resolvent and only for q equal to 2 upper star, actually in our situation. Yeah. But almost like this, we tried to write it up in such a way that you see that oft like LQ, L2 or L2, LQ upper star off diagonal estimates imply the LP bound. So actually, yeah.
Thanks.
So you know how to do it.
And as Eric said, this has nothing to do with resolvent or semigroups. This is just about operators.
Yeah.
These three.
It's a very general fact.
So, you still have a question? No? If there are no further questions, then maybe we should go to lunch. Thank the speakers again.